Digital data transmission is constrained by the capacity of storage hardware and network bandwidth. Every file sent represents a consumption of these limited resources. Traditional, uncompressed systems handle this data rigidly. They assign an equal-length sequence of bits, typically an 8-bit block, to every single character in a file. The system allocates those 8 bits, whether the character appears 10,000 times in a document or exactly once. To bypass this inefficiency, computer science relies on lossless compression. This is a protocol designed to reduce the total bit count of a file without discarding any original information. This table outlines our raw target dataset. We have a specific 6-character vocabulary and the exact frequency of each character: A at 5, B at 9, C at 12, D at 13, E at 16, and F at 45. Our objective is to execute the Huffman coding algorithm step by step on this specific dataset. By the end of the process, we will generate a bit stream that achieves the theoretical limit of compression for this set of characters. The algorithm dictates one strict design constraint to achieve this. The characters that appear most frequently must receive the shortest possible binary codes, while the rarest characters receive the longest. The algorithm begins by initializing each character from the frequency table as an independent leaf node. This horizontal min-heap pushes the smallest frequencies to the front. The algorithm greedily extracts the lowest nodes, A in 5 and B in 9, fusing them into a parent node of 14, which reinserts into the sorted array. It repeats this for C in 12 and D in 13, creating a 25 node. A crucial operational rule applies here. The algorithm is blind to the origin of the numbers. It strictly takes the 2 smallest values, making no distinction between a raw character node and a newly created internal parent node. By continuously combining the smallest weights, this bottom-up construction systematically places the rarest characters at the deepest levels of the hierarchy. The third aeration extracts 14 and E16, merging them into a node of 30. Next, it fuses the large internal branches, 25 and 30, into a parent holding 55. Finally, F45 combines with 55 to form the ultimate root node of 100. The algorithm hits its termination condition here. The execution loop halts the moment there is only one node left sitting inside the min-heap. That node becomes the root of the tree. The resulting binary tree mirrors the probability distribution of the data. The heaviest characters are near the top, while lightest weights settle at the bottom. With the hierarchy finalized, we can now map the physical tree into binary code. We apply a strict assignment rule to the connections. Every left branching edge receives a 0, and every right branching edge receives a 1. To determine the binary code for any character, we trace a top-down path from the root node to the target leaf. For our most frequent character, F, the path is minimal. Moving from the root directly down the left edge generates a binary code of 0. Contrast this with our rarest character, A. Tracing right, right, left, left results in 1100. When we compile the final Huffman code table, the structural logic is clear. F receives a single-digit code, while A receives the longest sequence. During the encoding phase, a message like face is translated by substituting the letters for their binary equivalents. F becomes 0, A becomes 1100, C becomes 100, and E becomes 111. These individual variables are then joined into a continuous bitstream cotransmission. When a computer receives that bitstream, it must determine where one character ends and the next begins without the use of spaces or separators. Huffman coding solves this by ensuring all outputs are prefix codes. This means no character's code will ever form the beginning sequence of any other character's code. To decode, the computer must always start at the root of the tree and read the bitstream exactly 1 bit at a time. The cursor reads the leading 0. It travels down the left branch, hits a leaf, outputs F, and snaps back to the root. Next, reading 1110, it traces the edges to the next leaf, outputs A, and resets. Because characters exist only at the leaf nodes, the cursor never passes through one character on its way to another. This prevents the machine from outputting partial or incorrect letters. This strict prefix property makes the sequence uniquely decodable, ensuring that absolutely zero data is misinterpreted during reconstruction. We can measure the efficiency of this process by comparing the uncompressed baseline data against the Huffman bitstream. The compression ratio is calculated by dividing the original size of 800 bits by our compressed size of 224 bits. This yields a ratio of 3.57, meaning the original file occupied over 3.5 times more space than the compressed version. Beyond file size, we must also consider the computational resources required to build the tree. The performance overhead is dictated by the min-heap operations. Because the processor must continuously extract nodes and reinsert them into a sorted array, the processing time scales logarithmically with the amount of data. In academic terms, the time complexity of Huffman coding is O of n log n, and its space complexity is O of n. A common error when evaluating this algorithm is attempting to assign binary zeros and ones to edges before the hierarchical tree is completely finished. Achieving optimal compression depends on strict adherence to these data structures and the exact chronological sequence of the build. The complete process follows 7 steps: establish the frequency, build the heap, combine the nodes, form the tree, assign the codes, encode the stream, and decode the result. By utilizing a greedy bottom-up construction, Huffman relies on character probability to dictate its architecture. The result is a uniquely decodable set of variable-length outputs that minimizes bit redundancy. This deployment of priority queues and binary trees remains an essential component in information theory, serving as the logic behind common compression formats used in daily data exchange.